It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Dave Ansell. Hi, Dave.
Hi there.
Now, coming up, the fly flu clue, how scientists have adapted the flu virus so it can infect insect cells, and that's actually helped them to uncover at least 100 new ways to combat the flu, which is good for this forthcoming winter. Also, how researchers in America have found a new way to turn their office windows into solar cells that can pump out power, and how scientists have also used muscle stem cells to treat mice with muscular dystrophy, and that suggests that the same trick might work in humans, and we'll be finding out how it works in just a minute. Dave.
Thanks, Chris. Now you need to strap on your trainers for this week's Naked Scientist, because with the Olympics about to kick off, we're looking at the science of how athletes use science to get themselves in shape for the big event. Plus, we'll be finding out how performance-enhancing drugs work and how scientists are hot on the heels of the people who are using them.
Thank you, Dave. You wouldn't use performance-enhancing drugs, would you? Now, talking about the science of sport, you're going to need a big bouncy ball and a tennis ball if you want to have a go at this week's kitchen science experiment.
3, 2, 1, drop. That almost hit you in the face.
Well, that's Ben and Dave dropping their balls in this week's Kitchen Science, and they'll be explaining what you have to do if you want to take part very shortly. Just grab a big basketball or a tennis ball, something like that. If you want to join in with the show in general, or you just want to say hi, we do love hearing from you. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Scientists this week have made a pretty amazing step forward when it comes to understanding how the flu works and grows inside our cells. This is Paul Alquist and his colleagues. They're based at the Howard Hughes Medical Institute in America. And what they've done is to convert a flu virus, which normally only infects humans and other animals like birds, into a virus that can infect insects. This is done by replacing the coat of the virus with the coat from another virus, the advantage being that this other virus does enable the flu to get into insect cells. And one other thing they've done is to add to the virus what's called a reporter gene. So if the virus switches on in the cell and grows, then it will make this other gene marker switch on, which they can detect. Now, why they've done this is that flies, in about the last couple of years, have had made for them the most powerful tool in the molecular biologist's toolkit, which is a whole sequence of tiny molecules called RNA interfering molecules. And every single one of the fly's 13,000 genes can be turned off selectively using one of these tiny molecular tools. So what this group did was to infect the fly cells with these modified viruses and then use these tools to switch off, one at a time and one by one, all 13,000 of the genes that run a fruit fly. And the idea of doing this is to try to work out what are the genes which are essential in a cell for flu to be able to grow. The results were really surprising. They found 100 genes which are in these insect cells, and because insects are actually very similar to humans, you can find a genetic counterpart of each of those 100 genes in our cells. And to prove the point as to how valuable this might be, they took 3 of the genes which they'd identified as being important, and in normal human cells, they turned off in turn each of those 3 genes and then infected the cells with normal flu viruses, and they were able to disable the virus between 10 and 20-fold in terms of its ability to grow in those cells, just by temporarily switching off those genes without necessarily producing ill effects in the cell that they did it in. So they're saying this is a big step forward because we now have 100 new targets we can look at to find ways to disable the flu and therefore potentially come up with new antivirals, especially with bird flu hovering on the horizon, because one of the viruses they tested was H5N1, what we think is the contender for the next pandemic.
I guess you've got to be careful that none of these genes are vitally important for running a body, so some of them won't be any use.
That's absolutely true, and it's a question of a toss-up between which ones are essential and which ones can be turned off, say, temporarily in order to disable the virus, and also which ones are only expressed in certain bits of the body, because flu only grows in your airways, chiefly the nose and sinuses. It's only in severe infections that it goes into the lungs, for example. So if you could find a way to, say, deliver a spray which turned off a gene just in those tissues and not affect the rest of the body, that'd probably be quite an easy way to do it.
OK, brilliant. Now, there have been hundreds of films and thousands of pictures made of dinosaurs, and scientists have carefully pieced together their shape and quite a lot of their lifestyle. But all of these pictures and films are missing one critical piece of information. What colour are dinosaurs? Now, the problem is that colours in mammals and most animals are produced by pigment molecules, and they don't survive the fossilisation process. So after tens of millions of years, you've just got sort of the imprint of the bones and maybe some imprints of the feathers and hair, but none of the actual colour is left. Now, Jakob Vintner and colleagues from Yale may have found a way of filling in some of these gaps for at least some dinosaurs. They've been studying feathers from some over 70-million-year-old fossilised birds from Brazil. They noticed that there were bands of small lumps of carbon running across the feather. Now, up until now, people thought these were just remnants of some bacteria which were eating the feather, and then the bacteria themselves got fossilised. But Jakob thinks they're actually fossilised melanosomes. These are small lumps within the feather which contain the dark pigment eumelanin, which is related to the pigment in your skin cells, which give you a suntan. This pigment is known to inhibit the growth of bacteria, and the parts of the feather with lots of these lumps seem to be much better preserved than the ones without them. Now, in modern feathers, the shape and distribution of these melanosomes will give colour to the feather. So dark feathers have got lots and lots of them, and some of the bright blue iridescent feathers have got what's called structural colour, which is where these melanosomes are very carefully patterned in order to reflect some colours but not others. Now, birds are dinosaurs' closest living relative, and several dinosaur feathers have been preserved in fossils, so there's no reason why we shouldn't be able to tell their colour from any melanosomes which are preserved in these feathers.
And that's the next step, presumably, to actually go and look at these fossils and see if they have the same structure, because that would enable you to sort of use the formula in reverse to predict what colour the structures must have been.
That's right. On the bird, they've worked out that it was a stripy feather with dark areas and yellow areas, but they haven't actually done it for dinosaurs yet.
Exciting stuff. Well, looking back at sort of more contemporary science now, scientists at Harvard have potentially come up with a way to treat at least mice, if not possibly humans, with muscular dystrophy. This is a degenerative condition of your muscles, which is carried on the X chromosome. So you inherit this from your mother, and you tend to get an excess of affected males, because men only have one X chromosome because their genes are XY. So if you have a defective gene on the X chromosome, you have no counterpart to make up for that. Women, fortunately, have two X chromosomes, so if they have a defective gene on one of them, the other chromosome can make up for the shortfall. So unfortunately, us guys draw the short straw here. But muscular dystrophy is caused by the loss of a gene called dystrophin. It's one of the biggest genes in the body, and it forms a cellular press stud, if you like, on the walls of muscle cells, which anchor the contractile filaments that make the muscle contract to the side of the cell. And if you don't have a working copy of that gene, then the cells deteriorate over time, and this leads to progressive loss of muscle and loss of muscle function, and this causes people to become disabled over time. How can we make this good? Well, what Amy Wagers and her team have done is to uncover from mice a population of stem cells in adult muscle, which are called satellite cells. Now, we've known about these satellite cells for some time, but what they've managed to do is to pinpoint a particular group of markers which are on the surface of these cells. That means they can selectively pick out certain ones of these satellite cells that can turn into new muscle. Because people thought in the old days that the muscle you were born with was the muscle that you had to make last a lifetime, and if you damage that muscle, you'd lost it. But now it turns out that's not actually true, and these stem cells can turn into muscle. And so by taking a purified stock of these particular satellite cells, using the markers they've identified, they then injected those cells back into mice which had the rodent equivalent of muscular dystrophy, and they found that over just 4 weeks they were able to rescue a muscle, and in the mouse's back leg, for example, 94% of the muscle fibres were replaced by these stem cells. And what that meant is that the force that muscle was able to produce went up by a factor of 6-fold to near normal levels. So it shows that, although they're not saying that in this paper that's in Cell this week, that this is going to be the cure for muscular dystrophy, they're saying we can identify what these stem cells are, we can purify them, and we can enable them to integrate into muscle and make good damage.
So, in theory, would you have to take cells out of your body, out of someone who's affected's body, then mend them somehow with some kind of process, and then grow them up and then inject them back?
One possibility is that you either make good the damage to that person's own gene and then put their satellite cells back in. Another is that you have a pool of these satellite cells which are in some way made genetically compatible with the individual, maybe a bit futuristic, but that's possible, and you'd then inject them. And because a muscle is what's called a syncytium, so in your body you have separate cells in some tissues, and other tissues, like muscle, you have all of the muscle cells merged together to form one giant cell, so they share their genetic material. And this means that you wouldn't have to hit every single cell. You just put a few of these stem cells in, they merge into the bulk of the muscle, and they transfer healthy copies of their genes into that cell, and this enables the cell to make up for the deficit of the dystrophin protein that was missing before.
Brilliant. Now, solar cells. Now, energy is a big problem, and solar cells have been put forward as one of the ways of solving the problem because there's an immense amount of sunlight coming down. The problem is they're very expensive and difficult to produce. Basically, this is because they've got to be made in a computer chip plant in a fab lab, and it's very difficult and expensive. So you want to maximise the amount of energy you can get out of each of these expensive solar cells. One way to do this is to concentrate the light onto the cell using relatively cheap mirrors or lenses. This means that several times more sunlight will fall onto the solar cell, so you get more power out for your money. However, the more you concentrate light using lenses or mirrors, the more accurately you have to point the whole system at the sun. This means that you need expensive and high-maintenance mechanical systems to point great big mirrors, always pointing at the sun at the right direction.
So what's their solution?
Well, Michael Curry and colleagues at MIT have got a system which will concentrate light whatever direction it's coming from. They've taken a sheet of glass and covered it with a dye which absorbs light at one wavelength and re-emits it at a slightly long wavelength. This re-emitted light comes out in all sorts of random directions, and about 80% of it gets trapped within the glass using a process called total internal reflection, which is what keeps light in fibre optic fibres. Now, you could do something similar by adding some dirt to the glass, and this would scatter the light, and a lot of it would get trapped in the glass. The problem is the dirt would then re-scatter this light back out again, and so overall you wouldn't actually get any concentration. What they've done is pick their dye so it will absorb light coming in, but it won't interact at all with the light which it's re-emitted. This means that the light keeps coming in and it gets really concentrated within this glass. You then get your solar cells, put it round the edge of the glass, and they'll generate about 10 times more
so the light travels inside the actual glass to the frame, gets sort of picked up and converted into electrical energy there, and then carried away to power things.
Yeah, that's right.
How efficient is this? How much energy could you produce?
Overall, it's about 7% efficient, which is about the same as cheap solar cells. But that means that you could probably produce sort of tens of kilowatts from a skyscraper if you made all the windows out of it, because not all the light's going to be picked up by this. And so you could just conceivably just turn all your windows on the south side of your skyscraper into these solar cells. And it would probably be quite dark inside, but you could probably optimise it so they don't, maybe slightly less efficiency and you get more light through.
As long as you don't end up having to spend obviously a lot more electricity to relight the office because you've blocked all the light getting in.
Yeah, there would be an optimisation
And then
process.
Everyone who's actually in the office gets seasonal affective disorder because there's no sunlight coming and they all feel miserable, and then your productivity goes down. Then you have to spend even more money, and it could be even worse for the environment in the long run.
But even if you didn't put it in an office, it would be a cheap way of making solar cells.
It could do. Now, also in the news recently has been how scientists, and we're talking about scavenging as much energy from the environment as we can to offset our carbon footprints and things. Well, scientists have now been exploring how they could use a giant rubber tube, which has been called the Anaconda, to generate electricity from the sea. And Professor Grant Hearn is from the University of Southampton. He joins us now. Hello, Grant.
Oh, good afternoon.
Welcome to The Naked Scientist. What actually is your device?
Well, the device is really was invented by Francis Farley and Rod Rainey, and essentially it's a long rubber tube, and it's closed off at one end and moored, and then at the other end you have a power takeoff system, and essentially you keep the rubber tube close to the free surface, and then and it's actually facing the oncoming waves, so if you like, it's at right angles to the wavefront, and as the waves come past the tube, then they set out what is called a bulge wave inside the tube. Now, as this bulge wave travels along the tube, it gradually gathers more and more energy. And so for one power takeoff system we've tried is that as the wave travels along the rubber tube, essentially you can convert that energy into potential energy by essentially allowing the water, which is being pumped, to go through a valve system, and you generate a high pressure level, and then you have a low level level, and you pass the water from one to the other through a turbine, and hopefully you then take the energy out of the bulge wave. That is.
And how much energy do you think you could make this way?
Well, what they're thinking about is devices which will generate of the order average of 1 megawatts, which may have a peak of 3 megawatts, but an average over a year 1 megawatts. And if you assume that you have essentially half a kilowatt per person, then that's basically one device would provide electricity for around about 2,000 homes.
And would you just have one tube in isolation, or would you have rafts of these out at sea somewhere?
You would probably have a farm, and at the moment what we're trying to do is we're trying to understand how best to operate the tube in terms of things such as the pressure in it. So the question would be, would you have tubes which are all identical, or would you in fact have tubes with different properties. So if you put a different pressure in, then you can take energy from a different wave frequency. And so what you might then do is to use a arrangement of devices such that they're all taking power from a mixed C state.
Okay, brilliant. There's been lots of other ideas of ways of getting energy out of waves. What's the advantage of the Anaconda over them?
Well, if we look back, sort of in the mid 70s, early 80s, most of them were mechanical devices. I mean, Salter's duct was essentially a set of segmented sections which rotated around a cylinder, and you essentially used the relative pitch of the ducts, as they were called, and the back spine to actually take energy out. Cockerel rafts were essentially using the relative motion of the rigid structure, so you have to have squash plates. And then I suppose then you have things like oscillating water columns. In this case, the only movable part is the rubber. So you're actually using the stored elastic energy in the walls of the tube to actually convert the energy external into the energy which flows internally.
So it should be a lot more robust. And finally, Grant, just very quickly, what stage of development is this at, and when can we see this actually out in the North Sea?
Well, I can't answer when it will be. If Rod Rainey and Francis think that once we've finished the work, it might be possibly 5 years. At the moment, myself with John Chaplin are entering a 2-year research program sponsored by the Engineering and Physical Sciences Research Council of the UK. And so there we're doing both experiments at different scales, and we're also developing mathematical models, because the difficulty with this structure is that we know the physical boundary conditions, but we can't actually put numbers on them. And so we have an interesting mathematical problem, which is how do you solve this problem and determine the boundary conditions at the same time?
Let's hope you get it sussed soon. Thank you very much. That's Grant Hearn from the University of Southampton telling us about their new Anaconda, which is a rubber tube that could actually help to solve our energy problems by promoting the use of wave energy.
The Naked Scientists. For more information, get online at nakedscientists.com.
It is The Naked Scientists with Chris Smith and with Dave Ansell.
Now, I think Pillay should be on the phone. Do you have a question, Pillay?
Yeah, what is the difference between cars that run on petrol and cars that run on diesel?
Hey, good question. The answer to this is it's a totally different fuel source. So the fuels totally differ in the way in which they behave inside the engine. Now, petrol engines have spark plugs and diesel engines don't. That's the simplest difference. In a petrol engine, what happens is that you have the piston going down in the cylinder and it pulls in some air, and at the same time some fuel is sprayed in if you have an injected engine, or it's just drawn in with the air as the piston goes down if you have a normally aspirated engine. The next thing that happens is that the piston goes up again and it compresses the mixture of petrol and air, and this makes it a bit warmer because when you compress things they do heat up, but it doesn't make it hot enough to ignite the petrol. And just before the piston gets to the top of the cylinder, the spark plug kicks in, ignites the spark, and what that then does is to ignite the fuel-air mixture, and this burns very fast, and this turns a liquid into a gas which takes up many, many times more space, and this increase in volume inside the cylinder drives the piston back down inside the cylinder, creating power. That's the power stroke. And then on the way up again, the exhaust valves open and you blow the exhaust out. So that's how a petrol engine works. Are you with me so far?
Yep.
Now, with a diesel engine, what happens there is that you're entirely depending on the compression of the engine to make the explosion happen. So what happens is the piston goes down. If you've got a normal old-fashioned diesel engine like they used to have on tractors and things, this just drew in a cylinder full of air above the piston, a bit like you pulling on a syringe and filling a syringe with air. The next thing that happens is that the piston would go up, and as the piston goes up, it compresses the air that it's drawn in. If you've got a turbocharger on your engine, actually what happens is that it forces a bit more air into the cylinder under pressure, so you have more air than you would normally have in the cylinder. Then as the piston comes up, it compresses all of the air, and when you compress air, just like putting your thumb over the end of a bicycle pump, it gets very, very hot. And the heat is hundreds of degrees Celsius, and just at the top of the piston compressing the air right at the top of the cylinder, the fuel pump turns on and it sprays a fine mist of diesel fuel into this superheated air right at the top of the cylinder, and this mist of diesel immediately starts to burn. And just like the petrol engine, it produces enormous amounts of gas. This expands very rapidly, and that's what produces the power stroke. No spark plugs in a diesel engine. That's basically, in a nutshell, the difference.
Okay, thanks.
Problem solved?
Yep.
Perfect. Good to have you with us. See you later.
Bye.
That's Pile, who is in Basildon. Dave.
Now, this week's show is based around the Olympics. So earlier this week, Ben and I raided the games cupboard and met up with some Cub Scouts for a sporty kitchen science.
Hello and welcome to Kitchen Science. Today we are with the 14th Cambridge Cubs, and in particular I'm with Nils. Hello.
Hello.
And I'm with Angus. Hi, Angus.
Hello.
So what is it that you enjoy so much about the Cubs?
You do loads of different activities. You learn new skills.
Well, I can see Dave Ansell with a basketball today, so maybe we're doing some sport skills. Hi, Dave. What are we up to today?
We're doing some interesting experiments on bouncing.
On bouncing. So are we going to play basketball?
Not really. A slightly strange version of basketball, if this is what you call basketball, Ben.
So, Angus, what do you think about basketball? You're a basketball player?
Yeah, I went to a tournament a couple of years ago.
Did you win?
Yeah.
Excellent, good for you. Dave also has a tennis ball. So, Nils, are you a tennis player?
Yeah, I have tennis lessons every Tuesday.
Excellent. So, clearly, Dave, we're going to be a little bit outmatched in this, but hopefully you've got something a bit unusual. So, if people are at home and they've got a basketball and a tennis ball, what do we need to do?
Well, you can use any large, heavy, bouncy ball and a smaller bouncy ball as well. What I want you to do is take the lighter ball, so I've got the tennis ball, put it above the basketball, and just drop the two at the same time and see what happens.
So you just place the small ball, in this case the tennis ball, on top of the basketball and then drop them?
Yeah, drop them so they both fall together and see what happens.
So, Angus, what do you think is going to happen when Dave drops them?
The tennis ball's going to fall off and bounce up higher than the basketball would, I think.
Nils, any ideas?
I think the tennis ball is just going to go in a different direction from the basketball because it's bouncing off the basketball, which is round, and it's got more bouncing space.
OK, so there's certainly the potential for balls to be bouncing around all over the place, and there's a couple of different ideas there about what will happen. It may be best, if you want to try this out at home, to do it outside, but we'll come back to you later on in the show and let you know what happened.
So if you want to try it out, you'll need to find two bouncy balls, a big one like a football or even better a basketball, and a small one like a tennis ball. What you have to do is put the small one on top of the big one and then drop them both, trying to keep them very gently as they drop down, so as they land on top of each other, and see what happens.
Fantastic. This is The Naked Scientist with Chris Smith and Dave Ansell. We're talking about the science of sport and the Olympics, and waiting in the wings is Dr. Chris Cooper. He's from Essex University. He'll be talking to us a bit about how you can improve your performance, but not necessarily the legal way. And so if you would like to join in with the show, the email address is chris@thenakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
This is The Naked Scientists with Chris Smith and with Dave Ansell. Dave, got an email here from Katie Giorgio. She's listening in Boston, Massachusetts, and she said, "Hi Chris, I think the show's great. I find myself thinking in a British accent after listening to your programme. What's up with that? I blame the media." Oh. She's got a little joke for us, and she says, "Did you ever hear about the two atoms that were walking down the street together, and one of them suddenly trips over and falls down and bounces back up and says..." It was your ball thing that made me think of this. She said, it suddenly says, "Hey, everyone stop, I think I've lost an electron." And the other atom says, "Dude, are you sure you lost an electron? Are you absolutely sure?" And the first atom goes, "Yeah, I'm positive."
Oh. Anyway, yes, and I've got another nice email here from Peter Blacksburg, who says, "Once upon a time we thought teaching science was important for education about 40 years ago. Bravo to you guys for a while, and once upon a time software was going to be educating. Unfortunately, everyone now plays shoot 'em ups. Then you came along and hope springs anew." So thank you very much, Peter, that's lovely.
Yeah, also thank you very much to Jennifer in St Neots, who congratulated me on becoming a dad again. Says she also likes listening to our programme. Thank you for that, Jennifer. And also Ian Hunt, who said thank you for producing an interesting and stimulating programme. So thank you, Ian Hunt. You don't say where you're from, but thank you. It's great to have you with us. If you'd like to drop us any lines, it's chris@thenakedscientist.com. Now, this week's show is all about the science of the Olympics and the science of sport, and we've seen news stories in previous Olympic tournaments where athletes have been caught using performance-enhancing drugs like steroids, for example, to increase their chances of winning. But how much of a boost is this really going to give them? Well, we've got Dr. Chris Cooper here from the University of Essex. He's going to tell us a bit more. Hi, Chris.
Hi.
So what's all this about? What sorts of things do people jam into themselves in order to boost their performance?
Well, all sorts of things. If you look at what Dwayne Chambers, the sort of current hot topic, he was taking at least 7 or 8 compounds. He was taking insulin, which diabetics take. He was taking testosterone. He was taking this thing called the Clear, which is this magic compound developed in San Francisco to not be detected by the drug detection agencies. He was taking thyroid hormone precursors. So they take all sorts of things, some of which work and some of which I think may or may not work.
So if I wanted to performance enhance myself, what agents would work in me? I mean, me as in the raw me, I suppose. Anybody.
So I think if you're unfit, lots of things will work, actually. The difficulty is if you're the super elite athlete. There are three general classes of performance-enhancing drugs. There's the anabolic steroids that you've probably heard of, the things that build up your muscle mass. There's the things that boost your aerobic sport. So the steroids help you for strength events. The compounds that help you in aerobic sports increase the amount of oxygen you can deliver, basically increase your number of red blood cells in your body. And then there's the stimulants, things like amphetamines, cocaine, modafinil, which is a sort of another very trendy drug. And those are a bit less clear whether they work or not.
I think they're more of a psychological effect, because a lot of people say that a lot of winning a race is 90% psychology, don't they?
Yeah, they are a psychological effect. Of course, psychology is just a branch of biochemistry. I'm a biochemist, so they're neuropsychology. But yes, whether the drug is directly working on the brain or the fact the athlete thinks they're getting an edge is an interesting question.
You think it might give them a sort of psychological angle, because an advantage, so they think they feel more confident, because winners win races, don't they? I mean, there's this sort of winning streak phenomenon where people feel a confidence boost because they win once, and this makes them win again.
Sure. I mean, there's clearly examples of people being given placebos, even in the Tour de France, which is sort of the drug cocktail par excellence. Some of the people have said, "Oh, well, I didn't want to give him this super cocktail of stimulants," and they gave him a sugar solution, and he won the race. So it's a combination of things, really. Yeah.
But looking at the agents that you can put into your body at the biochemical level, how do they actually work?
Well, there's been a lot of work on this recently, sort of an ongoing area. The steroids, the anabolic steroids, it seems that they work by increasing your ability to improve your muscle mass after you've done the exercise. So they used to be thought they let you exercise longer and harder when you're doing your weights, but now it's just thought they mostly work on the remodelling after the exercise. That's probably how the steroids work. The compounds that increase your oxygen capacity work by increasing your amount of your erythropoietin, and this is what's called EPO, and that controls your number of red blood cells. So you just basically increase your number of red blood cells.
And if you go and do what some people used to do, which is run up a mountain, so that you have altitude training on your side, how does that work? Is that particularly the same phenomenon?
Yeah, the key is not to run up the mountain, right? It's to go up the mountain and don't run there. So you go to the mountain, and when you're there, your body adapts to having a lower oxygen, because there's less oxygen up the mountain, and it makes more red blood cells. The problem with that is you can't train so well up the mountain. So the current idea is called live high, train low. You go up the mountain on a cable car, live there, and come down to the bottom for your training.
I did read somewhere someone had bought the equivalent of sort of oxygen tent for their bed, so that they could simulate oxygen levels at, say, halfway up Everest for sleeping, and then they would, of course, get out of their bed during the day and exercise at sea level, and this was supposed to do the same thing as going up a mountain.
Yeah, they're very common, easily bought, not that expensive, and not illegal. In the days of the East Germany, they used to have whole gymnasiums that were at low oxygen, where athletes just lived.
How can science also help athletes to do things the legitimate way?
Well, at the university, we do a number of things trying to mimic the effects that the drugs might have. I mean, there are things like trying to hyperventilate before you exercise, which changes your blood pH and means you can run 400 metres better. That's a sort of extreme version, which is quite difficult to do. Other things try and get you stimulated as equivalent to taking a stimulant. So you're trying to train to have the same chemical effect. And then there are legal drugs that you could add. You know.
Tell us a bit more about that. So if I was to start training now, what would be a sort of a good regimen for me, and what sorts of equipment could I use to make sure that I was effectively training the most efficiently?
Well, it would just depend completely on what sport you were going to do. I mean, if you were going to be a Paula Radcliffe, or if you were going to be a Linford Christie, what you would do would depend completely on that. If you were doing a power event, you'd be in the gym most of the time, especially in the off-season in the winter. If you were doing the long-distance event, you'd be running long distances, by and large. And then, of course, you'd have the nutritional team and the sports science team there working as well.
Mrinal Shah's on the line. Hello, Mrinal.
Hey.
Welcome to the Naked Scientists, calling from America. So where in America are you? It's a big country.
I'm in Troy, New York, which is upstate New York.
Well, welcome to the Naked Scientists. Got a question for Chris?
Yes, absolutely. I wanted to know if there were any natural steroids or there were only synthetic steroids, and also if there are any natural steroids, would it be possible for an athlete to get it in his daily diet? And if that would disqualify him from any sporting events?
Okay, that's a really interesting question. There are natural steroids. I mean, testosterone is a natural steroid. Obviously, men have more of that than women do. In terms of, and it's illegal to take testosterone because it's not part of your normal diet. It's difficult. You can't get a diet equivalent to fail a drugs test. So it's difficult to take a steroid enough steroids in any normal diet to have an effect because they don't work orally. You have to inject them. So then it's obvious, if you like, that you're doing the cheating. Where it's a more grey area is in some of the metabolites that the body makes from these artificial compounds, which are also illegal because the agencies say that means you've taken the metabolites. And there's a concern that if you exercise very hard and on certain diets, you might make small amounts of these metabolites naturally. So then it's a question of what level the drug company sets those at. But it's difficult to take a natural compound to fail a drugs test. And, of course, the bodies make it that way. They don't want to fail people for that.
There you go. Does that help you with that?
Yes, it was good to know a little more because the Olympics are coming up.
Yeah, you don't know what to avoid, do you?
Yeah, absolutely.
Thanks, Mrinal. Good to have you on the programme.
Thanks, Chris.
Mrinal Shah in New York. A quick question here for you, Chris, from Mario, and he's emailed to say, what's the fastest a human could run? Theoretically, what is the fastest a human could sprint at with the aid of all of the latest blood and drug enhancements?
Well, the cynical answer is to say we know that because we have the example. I mean, Tim Montgomery would be the example of somebody, but then he's been beaten by Usain Bolt. I think it's quite difficult question to answer. The world record now is 9.72, and no evidence that that's been done illegally. And you can sort of extrapolate from that as to where you might get. But I think increasingly we're going to see genetic anomalies, people who have got a genetic aberration or change that makes them perform better, and that's going to be what makes the difference. A classic example was a Finnish cross-country skier who had a naturally active EPO system, so he made in his body large amounts of red blood cells because he had a gene defect, or for him it wasn't the defect, of course. And I think you'll see these step changes by people who have just happened to have had a mutation. And it's difficult to therefore extrapolate to where we will go.
In this week's British Medical Journal, there is an editorial by Dominic Wells, who's at Imperial College, and he's saying, look, we're all worried about drugs and things, but how long is it going to be before people start doping themselves with genes? We know that certain genes definitely can enhance performance. How long will it be before people come up with ways to switch on or add genes to their muscles to make them more genetically fit, if you like?
Well, I'm sure people are thinking about this. I mean, quite often you read a scientific paper and you think, OK, that could help you in sport. And people who publish these papers, which are all done for medical reasons, suddenly get hordes of people, usually bodybuilders, contacting them and saying, how can I do this? So it's difficult, I think, but it's surprising that just changing one gene or up-regulating one gene seems to have an effect on human performance. I was surprised, but certainly if any of you go on YouTube, you can see this picture of this mouse that's had one extra gene put into its muscles, and it's running on the treadmill. It's going forever and ever, like a sort of the Duracell mouse. And so I think it's clear that the agencies, the World Anti-Doping Agency, have conferences trying to test for this, and it's going to be difficult. I think it'll be hard to do it because we can't even do it in medicine yet.
Thank you, Chris. That's Chris Cooper from Essex University. Troy McLuhan in Second Life has said maybe athletes shouldn't be allowed to exercise and train because it gives them an unfair advantage. What do you think about that? It is The Naked Scientist with Chris Smith and Dave Ansell. Still to come, we're going to be finding out from Diana O'Carroll in this week's Question of the Week how the Bornean flat-headed frog can breathe even though it's got no lungs, and we'll also be catching up with John Daniso, who works on how we test for some of the illegal agents that people can take to boost their performance. But we've also got a kitchen science experiment going. Dave, just remind people what it is you want people to do.
I want you to get a big ball, something like a basketball, a small ball like a tennis ball, two bouncy balls basically. Hold the tennis ball above the basketball, sort of chest height, and then attempt to drop the two of them as cleanly as possible onto somewhere solid to bounce off. Don't do this inside, do it somewhere outside with nothing dangerous to hit.
So if you've had a go at that, or if you want to send in a question or say hello, the email address is chris@thenakedscientist.com.
Laying the facts bare, The Naked Scientists.
This is The Naked Scientist with Chris Smith and with Dave Ansell, and we're talking about the science of sport, the Olympics, and how you can performance enhance by using various drugs and things. But this has become a major problem in recent years, and we need to know how we can detect when someone has been doing that. And someone who's working on ways to detect when people are cheating the system is John Daniso, and he joins us from the Sports Medicine Research and Testing Lab at the University of Utah. Hello, John.
Hello, how are you?
Very well, thank you. Welcome to The Naked Scientists. What sorts of agents have you been looking at?
We look, well, you just mentioned on the show some of the ones that are typically looked at. We test for things like anabolic steroids, both natural and synthetic. We look for stimulants. We also look for masking agents, which include things like diuretics, which sort of increase urine production, help people flush out their systems if they've taken something illegal. Also, for example, there's a compound called finasteride that is including in the masking agents, but it is a sort of it's a steroid metabolism regulator, and it actually decreases the production of a compound called DHT, which produces some of the secondary side effects of testosterone. But those are the main ones that we look for. Our lab's also working on some of the developing methods to look at, for example, homologous blood transfusions, human growth hormone, and things like that. So most of what you've been talking about we're working on in our laboratory right now.
The problem is, of course, if you take a drug, which is something that's naturally found in the human body anyway, how do you determine that that person has taken that illicitly and it's not just that they've got very high levels of that anyway?
Well, there's a couple of ways. For example, if you look at, say, testosterone, you just mentioned you couldn't get it from your diet, but there are, synthetically produced versions of testosterone. The big difference is that almost all synthetic hormones are produced from plant material, and plant material has a different ratio of carbon-12, which is the most abundant carbon isotope, to carbon-13, so a naturally occurring carbon isotope. And so one of the ways that you can test for that is using a carbon isotope ratio mass spectrometry. It's a method we're developing right now that most other anti-doping labs in the world have up and running, and we're very close to getting ours up and working right now.
What about if I say binged on testosterone? If I took lots of extra testosterone to bulk up my muscles, how could you find that and tell me that I'd definitely taken something from outside my body?
Well, one of the things we look at before the CIR test is something called the testosterone to epitestosterone ratio, or the TE ratio. And now epitestosterone is an isomer of testosterone, so it has the same chemical formula, but it's arranged a little differently, and it comes out at a different time in the mass spectrometry system. And most people have a TE ratio of around 1-to-1. They have equal amounts. It's been, there have been studies done that's shown that, some people have a little higher, have a little bit lower, but the World Anti-Doping Agency has set a TE ratio at 4-to-1 as a sort of cutoff, where if you have 4 times more testosterone than epitestosterone, that sort of raises alarm bells, and we can take that sample and investigate a little further.
So what would happen then if I took both? Because you can make both, presumably, and then the ratio would be normal. I just have very high levels. Exactly.
You can take both. However, there is an upper limit, sort of a ceiling for epitestosterone, where I believe it's 100 to 200 nanograms per milliliter. So you can't just take both, because then your epitestosterone level will be high enough that will also trigger a presumptive positive finding. And again, we can go and further investigate to see if an athlete has taken a synthetic version of testosterone, or epi for that matter. In addition to that, you get some of the metabolites of testosterone that, if we see those are elevated, some of the natural ones, for example, like DHT, again, that's another way that, we'll say, oh, this sample looks a bit suspicious. We always see a little bit of DHT, but if we see a lot, that could tell us, oh, they may have been taking something, so we can go and further investigate.
And just to finish off very briefly, John, what proportion of athletes do you think at some time in their career have probably used something?
I'm not sure I'm qualified to say exactly. I can tell you some of the, we have positive findings around, say around 2% of some of the samples that come through us. Obviously, one of the cornerstones of our lab is the confidentiality of the athletes, and so I can't divulge, what are the exact tests that we get, or what are the results that we get. But there's, in the low, certainly, I'd say 1% to 2% are some of the typical ratios that we see. And if you look on the WADA's website, you'll see other laboratories have about a similar percentage of positive findings. Now, I should emphasize that, these are the positive findings this is what's found by the laboratory. Somebody could be doping, if they're very, very sophisticated, they could be doping, at a level where they've, managed to, try to get around the system. That certainly happened with, the THG that was developed at Balco.
Let's hope that no one gets tempted. Thank you very much for joining us, John. That's Jonathan Dinoseau, who's from the Sports Medicine Research and Testing Lab at the University of Utah. Dave.
Now, another method often used by athletes to reach their peak performance is to use the best equipment or clothing on the market, whether it's the lightest bicycle or the toughest tennis racket. Having the best equipment on your side can make a real difference. So we sent Miriam Senthilingam along to Loughborough University, the home of sports science, to find out what makes a difference.
Performance sportswear plays a major role in the sporting events of today, and as a result, it's a growing field of scientific research. So this week, I went to the Sports Technology Institute at Loughborough University to meet sports technologists Dan Toon and Tom Waller to see what sports technology is all about. Here's Tom Waller.
Well, sports technology is one part of a very big machine of getting an athlete ready for race day. You think about it, there's sports scientists that will be dealing with their technique, their conditioning, their nutrition, psychologists to help them prepare for the day, and then we're dealing with all of their equipment. So any inanimate object that the athlete interacts with, from the footwear, the socks, the shorts, the compression apparel, the training apparel, rehabilitation aids, gloves, helmet, you name it. If it's something that an athlete has to interact with to carry out the sport that they're competing in, a sports technologist will have been involved in some part of that process.
So a lot of the projects you've been working on are helping our Olympians. What particular pieces of equipment have you been enhancing?
There's quite a big project going on with personalisation in footwear. But essentially what we're looking at is tuning the properties of a shoe to aid sprinting.
OK, so Dan, why is there a need to tailor footwear specific to athletes? Why can't they just wear the things that are available in the high street?
For an elite performing athlete, it's important to personalise the mechanical properties of footwear for maximal performance. To give you a little bit more detail, I've been particularly looking at the sole unit. And in a sprint spike, this differs significantly to standard athletic shoes. Standard athletic shoes have sort of an elastomeric or a sort of flexible sole unit, whereas a sprint spike is made up of a very, very stiff sole unit.
I can see, actually. So you've got some samples here, and the bottom is actually very solid. I didn't realise that sprinters' shoes were this hard.
Yeah, what I've actually been doing is I've designed a range of different stiffnesses from really quite flexible right through to something that is incredibly stiff, like you demonstrated. And then what I've had athletes doing is running in the sprint spikes and performing various jumps and various different sprinting-related tasks, and then measuring their performance in the different shoes, such that I can quantify how their performance differs.
So what's this actually doing to them, though, to their body or to their leg, in order to just overall make them a faster runner?
It really comes back down to sort of simple mechanics. If we look at the ankle joint, by increasing the stiffness of the shoe, what you're essentially doing is increasing the lever length about the point of application of force generation in the foot, about the ankle joint itself. And by making a shoe stiffer, you're increasing that lever length, and therefore they can generate energy more efficiently.
And how much of a difference has it made? I mean, have you seen a good difference in the people that have tried them?
Generally speaking, when we look at a comparison with a barefoot condition, by optimising the stiffness, you can probably expect to double the amount of mechanical energy that you can generate at the ankle, which makes a substantial difference to getting from A to B in a sprint race.
So, Tom, what makes this any better and, less immoral than resorting to drugs?
We're treading a fine line. When you talk about performance enhancement, you always raise concerns. Drugs, on one hand, are changing the human being. They're really changing the physiological makeup of that person, whereas we're bolting things onto the outside. So, for example, in Dan's situation, we're looking at the shoe and how we can optimise that shoe to enhance the performance of the athlete, but only within the rules. What we're not doing is putting giant springs on the bottom of their feet to make them jump higher or jump longer or run faster in that way. When we're put onto this planet, we're essentially naked. We're naked without any of these tools and pieces of apparel, footwear, equipment around us. And all of these sports involve things that we interact with. In terms of swimming, we wear hats, we wear goggles, because we have to cope with the environment that we're performing in. So we're making athletes more comfortable and we're helping them to perform at optimal levels.
Sounds good to me. Mira Senthalingham talking to Tom Waller and Dan Toon from the Sports Technology Institute at the University of Loughborough, and that's about the benefits of personalised sportswear in athletic performance.
And now it's time for Diana Carroll with Question of the Week.
Hello. Well, this week we're going to be leaping into a breathing issue.
Hello, my name is Jason Flakes, and I'm calling from Annandale, Virginia. My question is how is it possible for a Bornene flat-headed frog to have no lungs and breathe through its skin?
Other frogs have lungs to help them ribbit, so why is this one different?
My name is David Bickford, and I'm an assistant professor at the National University of Singapore, and I was a member of the team that recently rediscovered the species and was able to actually find out that it doesn't have any lungs. First and foremost, the ecology of the animal, where it lives, are extremely fast-flowing streams that are clear and cold. They're coming right down off of the largest mountain in Kalimantan, Bukit Baka, and the cold water actually holds more oxygen than warmer water. And when it's traveling very fast, the frog is able to basically run into more molecules of oxygen as it's carried in the water. Also, most amphibians are able to do most of their gas exchange through their skin anyhow. Lungs in amphibia are fairly primitive, and they mostly just get a little bit of oxygen through their lungs. They get rid of most carbon dioxide through their skin anyhow. So what is probably the real kicker, the real reason that these guys don't have lungs is that same very fast-flowing water could be detrimental to you if you got swept away. And a good way to get swept away is to be buoyant or to float in the water. So having lungs makes you a lot more buoyant. It's kind of in the context of very fast-flowing streams that these frogs need to do everything that they do. So it's easy to imagine that being a very strong selective force.
The frog has a clever adaptation for the fast-moving water in which it lives. Instead of using air to obtain the oxygen it needs, it relies on enough water hitting it every second to receive the required amount. The frog can also breathe through its skin, which has tiny blood vessels or capillaries for oxygen exchange. If the frog did have lungs, though, it would float to the surface and be swept away downstream, a bit like a poo stick. Well, that's one exciting adaptation, but how's this for a step in evolution?
Hi, it's Jeff Blackwell calling in from Bundaberg in Queensland in Australia. I'd like to know if there are any life forms, plant, animal, fungus, whatever, that are effectively immortal.
From an age-old life form to some paleontological recycling.
My name is Sky. I'm an archaeologist in Arkansas in America, and I was taught when I was young that we drink the same water today that the dinosaurs drank when they were alive, and I wondered if that was true.
So, what is the oldest water that you have consumed, and who is the oldest person that you know? Drop us a line at questionoftheweek@thenakedscientist.com, or you can even write your ponderings on our forum at thenakedscientist.com/forum.
Thank you very much to Diana O'Carroll for this week's Question of the Week. I'm just having a sip of some dinosaur urine here in the studio, assuming that's true, of course. Thank you, Diana. It is The Naked Scientist with Chris Smith and with Dave Ansell, and we are talking about the science of the Olympics and science of sport and how you can use drugs and things to boost your performance.
Time now to go back to the Scout Hut in Cambridge where Ben and me were experimenting with the science of bouncing.
Welcome back to this week's Olympic Kitchen Science. We are still with the 14th Cambridge Cub Scouts, and I'm still with Dave Ansell, who's got a basketball ball and a tennis ball. You could do this with maybe a football and a tennis ball, or anything that's good and firm and will bounce quite well. And what we want you to do, put the tennis ball on top of the basketball, drop them both together, and see what happens. Now, we're going to do this with our volunteers Nils and Angus today. So, Dave?
OK, Angus, if you'd like to take the basketball, and Nils, if you'd like to take the tennis ball and balance it on the top, and just hold it so you're not holding it up, just put your finger on the top to stop it falling over. Then I want Angus to drop the basketball as cleanly as you can. Just take your hands away from it and see what happens.
OK, then, Angus, are you ready to drop?
Yeah.
And you still think that they're going to kind of roll off each other and bounce somewhere else, but the tennis ball will bounce higher?
Yeah.
OK, and Nils, you still think that the tennis ball's going to shoot off in some random direction?
Yeah.
So if everyone's ready, it's 3, 2, 1, drop. Crikey, Angus, that almost hit you in the face. What happened there?
It flew off before the basketball hit the ground and bounced off in a random direction, and the basketball still bounced, though.
Okay, and how high did the tennis ball go?
It hit Angus in the shoulder, which was, so I say that's pretty high.
Well, you dropped it from around chest height, so it certainly went higher than you dropped it from, didn't it?
Yes, definitely.
Now, I don't like to be rude, Dave, but Cub Scouts are somewhat shorter than you, so would this be a more impressive experiment from your chest height?
I can try it if you like.
Okay, once again, we're going to try this from a bit higher, and now I want you to tell me what happens. So, 3, 2, 1, drop.
The tennis ball has bounced off, and Niels is now playing with the basketball, and the tennis ball has gone into a bush.
Well, while Dave manages to find the tennis ball, which is now buried somewhere deep into a bush, one thing I noticed, did you see how fast the tennis ball shot off the top of the basketball?
Yeah, it's like it flies off as though it's just been pushed up by something, and the basketball flies down.
How high did the tennis ball bounce?
Way above Dave's head.
It was a long way above your head, Dave. And in fact, even though it's been shooting off towards people's faces and shoulders, one thing I've noticed is it always bounces a lot higher than the height you dropped it from. What's going on here?
Well, normally when you drop a ball, it will bounce less high than it started, because some energy is lost in the collision.
So that was dropped from roughly chest height and it bounced up to just over waist height. So yes, it always seems to bounce lower than it was dropped from.
OK, Niels, you said you're playing tennis. How fast does a ball bounce off if the tennis racket's moving towards it when it hits it?
Pretty fast, yeah.
If you throw a tennis ball at a tennis racket and the tennis racket's stationary, then the ball bounces off quite slowly. However, if you move the tennis racket towards it, the ball's going to bounce off much more quickly. Now, with this basketball, when it bounces off the ground, all of a sudden it's moving upwards almost as fast as it was falling downwards. So it's a bit like a tennis racket moving upwards. And the tennis ball drops and collides with that, so it's going to bounce off much faster than it was falling.
So it's a bit like the basketball is acting like the tennis racket, in that it's hitting the ball quite hard, and that sends it off quite fast.
Yeah, that's right. Imagine both balls are moving at 1 mile an hour when they hit the ground. When the basketball bounces up, it's now going to be going nearly 1 mile an hour upwards, but the tennis ball's still doing 1 mile an hour downwards. So it's a bit like a tennis ball hitting the basketball stationary doing 2 miles an hour. And because the basketball's moving at 1 mile an hour upwards, the tennis ball should be moving upwards at nearly 3 miles an hour. So it should bounce upwards nearly 3 times as fast as it came downwards.
But if the tennis ball is moving down at 1 mile an hour and the basketball's coming up at just under 1 mile an hour, why don't they just cancel out? Why doesn't the tennis ball stop?
Well, because the basketball's moving towards it, then there's more energy there, and then that energy is going to get reflected in the collision, and it's all going to get transferred to the tennis ball, so the tennis ball will go really high.
So what do you think of that, then?
I think it's very complicated, but I think I just about understand it.
Cool, I'm pleased to hear it. And do you think this will affect the way that you play tennis?
Probably, yes.
Well, thank you very much for joining us for this week's Kitchen Science. We better let you get back to Cubs, so thanks very much. Goodbye.
Bye-bye.
Well, that's all for this week's Kitchen Science. We will be back next week with another exciting experiment.
So the bigger ball bounces back up, hitting the smaller ball, sending it flying away 3 times faster than it was falling. Ben will be back with more Kitchen Science next week.
Thank you very much, Dave. It is The Naked Scientist, Chris Smith and Dave Ansell. We're talking about the science of sport this week, and we have with us Dr. Chris Cooper, who's from the University of Essex, and he's a biochemist who works on how the body responds to exercise and that kind of thing. Got a lot of interesting questions coming in for you, Chris. In Second Life, Aviator Shepherd says, can we not just monitor athletes to see how their metabolism is performing and then regulate it so that everyone has the same level?
Well, that's a really interesting question. It's kind of like the athlete having a passport, a sort of biometric passport, that says they're all the same level, sort of treating them like a Formula One car. And in fact, something of the sort is used in cycling at the moment and in cross-country skiing, where if you have too many red blood cells, your hematocrit's too high, you can't compete because it's assumed it's unsafe. You might have a heart attack, but you're not banned.
But in reality, someone's probably just banked a unit of blood a few months ago, built their blood back up, and then reinfused it before the big race to boost their oxygen-carrying capacity of their blood.
Yeah, but if you set the level low enough, then they will fail. So that's the trick, is to set it
Absolutely.
at a fair level.
I've always wondered something. If you were a really evil athlete and you had a big competitor, could you drug their drink in the pub the night before the event and then they get knocked out of the competition?
There's always claims. I mean, Ben Johnson always thought that's what happened to him. It's not clear that was. And Dieter Baumann, a famous West German runner, claimed he was doped in his toothpaste. And there's some evidence that was the case. So if you're running a marathon, you always take your drink. It's always your own drink and it's always sealed. and then you take it. So you don't just take drinks lying around. People are concerned about it.
And what about this question of natural levels of testosterone and things like that? Pookie Amsterdam in Second Life says, are there just some people who naturally have above average levels of testosterone and that's what gives them the advantage?
Well, there are certainly some people who claim that. And I'm reminded of this great, actually true story about one of the US Olympic 100-metre sprinters who failed the test that Jonathan talked about, having too much testosterone. And in his defence, he said, well, it was his wife's birthday, so he had to have sex 5 times a night the night before, and that's why his testosterone was so high. And he got off. Nowadays...
In more ways than one.
Well, she got... Yeah, anyway, yes.
And is that true? The
story is true.
I don't doubt the integrity of the story, but is the actual effect true?
I think your testosterone can vary depending on whether you're having sex or not by the amount that he claimed. So I don't think you can use that as a performance-enhancing effect. It might not be a good idea the night before a race.
Although football coaches do say that their players should be banned, but how many of them actually are, who knows?
And we've got a question here from John from Colchester. He's wondering whether now drugs seem to be getting stronger and stronger and more common. Could they be excreted and end up in our water supply?
Well, that's an interesting question. I mean, there's always scare stories about what's in my water, what harm it's doing. There's a long-term slight concern about female hormones getting into the water supply, very, very low levels. I think that's not likely to be a big health problem, but certainly there have been concerns in the past. In terms of drugs and sport, there's no way you can get enough drugs in your water supply to help you in sport or to fail a drugs test. So that's the sport part of that question is not a problem. The general human health one is a whole other major issue, which I think is probably overstated, but it is out there.
So Thames Water probably off the hook then. Got a question here from Robert Riley for you, Chris. He says, is it faster to run barefoot? He says, I run on my local sports track a few times a week. I've been doing this for years, trying to beat my personal best of, say, 2:40, but to no avail. Then last month, on a whim, I decided to run it barefoot, and I ran 2:34, which was totally smashing my personal best. I've tried it a few times again, and have again run 2-minute 30s. As an experiment, I ran my next few times in trainers and ran low speeds again. So, is running barefoot faster for me, and if so, why?
Well, I mean, clearly it is faster for you because you've just given us the scientific evidence that you feel you run faster, or you do run faster when you're in barefoot. I don't think, in general, running in barefoot is faster. I mean, the historical example is Zola Budd, who was South African, then came to run for the England, and she ran as fast, I think, in barefoot, and she would have been much worse running in shoes because she wasn't used to running in shoes. I think for your kind of event, if it doesn't have an effect, then that's fine, as long as someone doesn't step on you when you're running. For sprinting events, I think the shoes are really important, and I would be very surprised if you could run 100 metres in barefoot as fast as you could without. But
as we heard from Mira talking to the Loughborough team, showing that you get far more force produced because of the ankle articulation, because of the stiff-soled shoe, compared with barefoot, or even a pair of trainers that are fairly soft.
Sure.
I guess maybe he might just be wearing very bad shoes, which is slowing him down.
Yes, that's another thing. I assumed he wasn't, but yes, that's a possibility. Just get a new pair of shoes, yeah.
Thank you. That's Chris Cooper. He's from the University of Essex, and also on the programme, John Daniso, who was working on drug testing, and we heard from Grant Hearn with his new way of generating electricity into the future. Thank you very much also to our wonderful production team, Ben Valsler, Diana O'Carroll, and our production hot seat victims this week, Petra Minch and Mira Senthilingam. Next week, we are exploring the science of drug discovery, so in other words, looking at how we develop new drugs and how we can take the genes that turn into proteins in cells and use that information to make tailor-made drugs that can very specifically target certain things, including infections, and we'll be finding out about that next week. If you have any questions for us on that, send them now, chris@thenakedscientist.com. Now, finally, we do have a very big favour to ask you this week, which is that we're always trying to make The Naked Scientists even better, and that means we really need your help to tell us what you do and don't like about our programme. So we've set up a simple online survey. That's at nakedscientist.com/survey, which has a number of little tick boxes and only a few pages, so it'll only take about 5 minutes for you to fill it in. And we'd be very grateful if you could give us your objective feedback on what you think of the Naked Scientist website and our podcast. Now, as an added incentive, this is special, we're going to give away the first ever new Naked Scientists t-shirt, which is bearing our brand new logo, and that hasn't been unveiled yet, so you'll be able to get one of those. And we're also going to give away a copy of Crisp Packet Fireworks, which is our kitchen science book that Dave Ansell and I have now written, and that hasn't even come out yet, so you'll get a signed copy of that too. And there are also copies of Crisp Packet Fireworks as 10 runners-up prizes, and we'll sign those too. So that's at nakedscientist.com/survey. We'd be really grateful for your help. Please take a look at it if you can. Have a great week. See you next time. Goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.